Okay, have a look, please. Okay, so here's some stuff from the 6.2 assignment. Let's just quickly, we'll use this to review some properties of parallelograms. Okay, so if we know that, let's see here, if we know that, oh, okay, I need to tell, I'll have to add this to the text. This is a parallelogram. Okay, so we're dealing with a parallelogram. That's assumed. Oops, there we go. Okay, so what are some properties here that might be useful? If I know it gives me lengths of hi and ij and jk and hk, what's something useful about a parallelogram that might be helpful here?
The two sides that are parallel to each other.
Okay.
So like HI and KJ.
Okay, so that's one thing that's true. These are, we know in a parallelogram, these sides are parallel and those sides are parallel. Okay. Something else. What do you think, Kirk?
Parallel sides are congruent.
Okay, the parallel sides are congruent. Okay, now that might be even more useful. So then we know that this side's congruent to that side and that side's congruent to that side. And so what could I do with that? So I could set the measures. It's giving me the lengths of those sides, isn't it? Right? So I could set those equal, and I'm going to get two equations then, right? What's one of the equations? How about if I set the vertical sides, the lengths of the vertical sides equal? What am I going to get? So HK and IJ. So what is that? Negative 9x plus 3 equals negative 8x plus 7. Easy, right? How many variables in that equation? We can solve for it, right? No big deal. The other equation I'm going to get, let's see, I'm going to get
2y plus 5
equals
3y minus 12.
one equation in that one, no big deal, right? We were able to solve for both variables, piece of cake. Not a big deal. Okay, how about, that's not very tricky. We need one a little trickier than that, don't we? No. Okay, what about this guy? Once again, it's a parallelogram. I need to change it to just tell you it's a parallelogram to begin with. So this time we're looking at HG. So we've got this segment and IG, this segment, HJ and IK. What might be an important relationship here? Sir?
HG is 1/2 of HJ.
Okay, so, but what's the,
It looks like, but we don't know if it is.
okay, but, so if it is a parallelogram, let's just start with what we do know. What do we know about, what are these things called? The diagonals. What do we know about the diagonals of a parallelogram?
They bisect each other.
Okay, good, they bisect each other, don't they? Right, so if they bisect each other, then doesn't that mean that that segment and that segment have to be congruent, right? And that segment and that segment has to be congruent, right? And so now I should be able to set up something here, right, where I've got, like for example, HG, that's this distance, compared to HJ would have to be what? Have to be half, wouldn't it? Right? Because if these are equal in length, then HG is only half as big as HJ, right? And so we could set up some kind of a relationship here where like HJ is equal to 2 times HG. Once again, it's only one variable though in that equation. Piece of cake, right? Okay, well that's not tricky enough. That's not even remotely tricky enough. Okay, so what about, once again, a parallelogram. Okay, look this time. This is a little trickier, isn't it? This time it looks like it's going to be easy. We got HI and IJ and JK and HK. But now when I set these opposite sides, the length, they're congruent, right? The lengths equal to each other. What happens? Oh, I got two variables. Yikes. So I get the equations. Here, whoops. Oh, that's not what I get. I get the equations. So let's make the blue ones lengths equal. So HI should equal JK. So those two are equal, right? And then the red ones are equal. So IJ equals HK. And so you're gonna have to figure out a way to solve that. Don't say anything. I want everybody to get a chance to figure that out. But that's right. So that's a little tougher. But once again, it just relies on some properties of parallelograms. So real quick, let's just remind ourselves, what do we know for a parallelogram? What are the properties of parallelograms? We already said one. We know opposite sides are congruent. What's something else? Opposite angles are congruent. Okay, opposite sides are parallel. That's going to fall under, really, that's not, we wouldn't consider that a property. That's actually the definition of a parallelogram. So the definition is opposite sides are parallel. Okay. Give me another property. I want another property. Brooke, what do you think? You remember one? Opposite sides are congruent, opposite angles are congruent. Are there any others? Emma, you got one? Parallelogram? What about, there's another one involving angles. Another one involving angles. Oh, okay, good, yeah. We know that consecutive angles are always going to be supplementary, aren't they? Okay, so there's another one. Consecutive angles are supplementary, and what's the last one? I think we already mentioned it. What's the last one? Okay, good. Diagonals not intersect, they bisect. Good. Okay, good. All right, so section 6.2 is just about using those properties. And probably the hardest problems, like you might expect, are going to be the problems where you've got to take those relationships, which aren't really that tricky, and do some algebra based on those relationships. 6.3, like we often do in geometry, 6.3 is about kind of turning the tables. And now we're not going to be given that the parallelograms, or that a quadrilateral is a parallelogram. We're going to try to prove that it's a parallelogram. Okay? So I want you to hypothesize something here. If I've got a quadrilateral, and this is my quadrilateral, what's one way that you can, right now, for sure, prove that it's a quadrilateral? I mean, that it's a parallelogram, sorry. So we're trying to prove. What is it? Yeah, if we can prove that it contains two pairs of parallel sides, it's a quadrilateral, then by the definition of a parallelogram, we got it, right? That's not always convenient, but that's one way we could always do it, right? Because we know the definition of a parallelogram is clear cut. And we want to hypothesize maybe another way that we could do this. What do you think? Hypothesize another way. Somebody that hasn't offered anything. Can you give me I mean, it might be wrong, just a guess, but what do you think? What seems intuitively like another way we could maybe show that this is a parallelogram?
Something
About the angles, there's something there that would work. You got an idea? Okay, we could, there's another way we could do it. it turns out, and I want to go ahead and prove some of this stuff, but you're right. We could say that if the diagonals bisect, then it ends up being a parallelogram. That's true. Are you noticing a pattern here? Yeah, they're just same relationships we just had, reversed, right? So it turns out that you can take the converse of all of these, and it works. Okay, now, one in particular we have to be a little bit careful with. Okay, but that's, so we're going to get all of those and some more. Okay, but probably the first and the easiest one might be that if the opposite sides are both congruent, then it's a parallelogram. Doesn't that seem like that should be the case? And it is, but we don't know that yet, do we? Right? I mean, it turns out it is going to be a theorem that's going to be added to our list, but we probably should prove that, right? That if this is true, if this is what's given, then it's a parallelogram. Okay? Let's try that. Let's try that. So see,
Couldn't you have a rectangle to add?
you could. That's true. Ah, okay. But what do you think? A rectangle. That makes sense?
Yeah.
Okay. Okay, so let's look at our stuff here. So given, sorry, not given. We want steps and reasons, right? We'll make this a 2-column proof. We haven't done this in a while. We need to get kind of back to proving some stuff. So what's probably the first thing? Okay, and technically we're given the congruences, right? So we could say side AB is congruent to side CD.
Yeah.
And side AD. Okay, and our reason for that? Given. Suggestions? Think of something else. And at this point, what's our only way to show, until we start getting some of these other shortcuts, what's our only way that we know for sure we can prove this is a parallelogram? Say it again. Well, okay, we're gonna kind of show all of these can be reversed, and this is the one that we're reversing right now, isn't it? If opposite sides are congruent, we're gonna end up proving then it's a parallelogram. Right, but we don't have that yet. But there's something that for sure we always have.
So, can you put in the page?
For?
The one that we were on. Okay. So if AD plus DC equals AB plus DC, might that mean that ADC and ABC are the same angles then?
Well, I mean, maybe we'll get into specifics, but we got to kind of have maybe a little bit of a strategy in mind here. We don't yet have any of these are really not fair game yet. So we're going to prove them. I mean, they're in the book, but we're going to prove, not all of them, but maybe we'll prove a couple of them at least. And then once they've been proven and we can add them to our list, then they become reasons. But let's just pretend that we don't have those reasons available yet. We're going to try to prove this one without using any of the other ones. What's the only way that we could really prove something is a parallelogram at this point, without any of the shortcuts?
Could you do something with the crossing lines?
Eventually we'll be able to maybe turn this one around.
Prove all the opposite sides are.
Yeah, but by definition, a parallelogram is a quadrilateral where opposite sides are parallel, right? So if we could just show that the opposite sides are parallel, we'd have it. Agreed?
Yeah.
Okay, so now that's our strategy. If we could get to that point, we would prove that it's a parallelogram. And then we've got, and think how general this is. The only thing that we've been given here is that opposite sides are congruent. So this should work for any conceivable quadrilateral with opposite sides congruent. It's going to be completely general if we can prove it, right? So what could we do? Ideas, just throw something out here. What could we work with here? Think about the tools available to us to prove things, the relationships we know about. What do we know an awful lot about? Triangles. Yeah, we know a lot about triangles, don't we? We have lots of congruence relationships for triangles. Okay, so what do you think? Suggestion?
Should we bisect it and then,
By bisect it, you mean, could we maybe
or I mean, yeah.
sure, yeah, we can always drop in a segment. That's right. We know that point A exists and point C exists. So, for example, we can add that. That's fine.
Would there be a reason or something for that? Or
Well,
would
I
you
mean,
drop?
I mean, if you're going to be really in college, you'll probably have to maybe include the reason that there exists a segment between them. But we're not going to. It's pretty intuitive that if there's 2 points there, by the definition of a segment, we could always just add a segment. If you're going to get really nitty gritty on proofs, you'd want to add that by the definition of a segment, it could exist. But I don't want to bog it down with all those really kind of insignificant. I just want to get the big picture going. But that's a good question. So it exists. There's our segment AC.
You can prove that triangle ADC is congruent to CBA.
Okay, how come?
Because since they're middle.
Okay, so we do need one other thing, don't we? We need that this segment is congruent to itself by what property? Reflexive property, sure, okay. So segment AC is congruent to itself by reflexive property of congruence, right? Good. Okay, now we've got 3 sides in one triangle congruent to 3 sides in another triangle, so we can show that the triangles are congruent. That's good. All right, so Kurt, I'll be real careful here. How am I going to say that congruent statement then? Triangle ABC is congruent to triangle, yeah, does that make sense? CDA, okay? Does everybody get that? Because in the top triangle, vertex A is the vertex that's pinched between 1 hash and 3 hashes, right? So in the bottom triangle, the vertex that's pinched between 1 and 3 would have to be C, right? So triangle CDA, and that's by what? Side, 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 congruence. Okay, now what? Okay, yeah, what can we, very good. So now that we know the triangles are congruent, there are 6 congruences that are carried with that. 3 of them we've already got, but we've also got the 3 angles, don't we? Right? So let's lump those together maybe. So what are some angles that might be useful here to show are congruent?
Angle B is equal to angle B.
Okay, angle B is congruent to angle D, okay? Angle B congruent to angle D. And while we're at it, what else?
Angle A.
Okay, so for A, you gotta be a little more specific. Which angle A? BAC, I heard. So we'll take that one, that's fine. That one we can kind of, now that we've chosen BAC, we gotta be careful. So angle BAC is congruent to angle AC, say it again, BAC and ACD, there we go. Yeah, that's supposed to be a D, right. Okay, and then one more, so I guess we got, well, let's write those up there. So we got this one congruent to that one congruent to that one, and then
BCA and DAC.
okay, good. And we can do that by CPCTC, or we could even use, remember the third angle theorem? I don't know if we've ever even used that one, but remember, can someone tell me what the third angle theorem is?
So like 2 angles. If we know 2 angles, the third angle is done.
Okay, good. If 2 angles in a triangle are congruent to 2 angles in another triangle, then the third angles have to be congruent, right?
Let's go to third angle.
Third angle theorem. Yeah, here we can just use CPCTC though, right? So the other one we get is this guy and that guy, right? So what is that? ACB congruent to DAC. And those are all lumped under CPCTC. Good. Okay, well that's pretty helpful. Now I think we should be able to show some parallelism. What do you think, Elton?
Take using the opposite interior angles
Okay.
and prove that the segment DA is parallel to segment CV.
Okay, so let's kind of color code this one. So if we take these two angles, how about? Those are alternate interior angles of these parallel lines and this transversal, right? Everybody see that? Okay. So then we know that segment AD is parallel to segment CB. Okay, by what?
Opposite interior.
Okay, alternate interior angles,
Converse.
converse. Good. In college, just so you know, I want you to have heard this once. In college, wouldn't you agree that all those angle, at the time they seemed like a pretty big deal, but now we just, don't you almost in your mind kind of lump all those together? Like if parallel lines are cut by a transversal, then corresponding angles are congruent, alternate interiors are congruent, etc. In college, when you're taking a geometry class, you will probably call all of those capital ALT. Capital ALT a lot of times in more advanced math class stands for all of the relationships that start with if two parallel lines are cut by a transversal. Okay. All of the other ones that prove parallel lines, like the alternate interior angles converse, or the corresponding angles converse, or consecutive interior angles converse. Alex, put that away, please. All of those we would call all capitalized conal, or converse of all. So you'll see those again probably at some point. But just so you've heard it once. So this one was alternate interior angles converse. Well, while we're at it, is there another set of angles we could show, another pair of lines there? Yeah, we could also show if we used, like, for example, these angles. Whoops. If we use these angles, right? Then we could show these are parallel lines, and that's a transversal, right? Does that make sense? Oops. So this would be also segment, what are we doing, AB? Gosh, why did I do that? Is parallel to CD. And now we got it, right? If those are parallel, and those are parallel, I can't fit the last step on there, but what is it? ABCD is a parallelogram by definition of a parallelogram, right? Okay, make sense? Okay, so we proved this one has a converse, right? That works. We could show it for all of them. We really could. We could show it for all these. But those are all relationships we can reverse and use to prove parallelograms. There are a couple other ones we get. I think only one of them we're going to use now. Yeah. That's also you can use. This is kind of a tricky one. So we can turn all of these around. Those are all have converses, just flip them around. And you know what I mean by that? Instead of saying, if opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. We would say, if, got that backwards. If a quadrilateral is a parallelogram, then opposite sides are congruent, is what we did, right? So we could summarize that by saying, if parallelogram, then opposite sides are congruent, right? The converse of that would be, if opposite sides are congruent of a quadrilateral, right? Then parallelogram. Does everybody see that? That's what I'm saying when I say we're going to do the converse. Here's an extra one we get, though. Here's an extra one we get. If we have a quadrilateral and two sides of the quadrilateral are simultaneously parallel and congruent, that's enough, believe it or not. That's enough to show that it's a parallelogram. Okay? So if two sides of a quadrilateral are parallel and congruent, then it's parallelogram. Let's prove that one. That's going to be a little harder to prove, I think. Yeah, that's a little harder to prove. At least let's talk through it, talk our way through it. Oh, you want me to go back? Okay. Okay. All right, so let's label this stuff. So here's our quadrilateral. We'll just call it A, B, C, D again, how about? And this is what we're given. Take a second and just see if you can come up with a strategy. See if you can come up with an idea about, maybe sketch some things on there. See if you can come out with a reason we know. Given AB, side AB is congruent to side CD, and side AB is parallel to side CD. Okay. See if you can come up with a strategy. Oops. No Duncan today? Is he sick again, or is, wait, no? He was, yeah. Hope he didn't get sick again. Oh, man, okay. So, oh, so that's what I didn't know, so that's why he was, okay. Okay, what do you think? Any suggestions with this one? It's going to be kind of a similar thing, isn't it? Suggestions. Let's get somebody. Daphne, what do you think?
Can you extend the lines, then, like line AB
okay.
and DC, and so then angle CB and whatever that went off there, so that angle be the outer angle, and that would equal angle C inside.
Okay, say it again.
So if you extend the lines.
So if we extend these and make this a transversal, for example. So if we're doing, oops, oh, it's frozen. Okay, this is a different way of doing it. This is good though. So extend these two and make that a transversal. Okay, then we know we have parallel lines cut by a transversal. So what do you know?
So then angle CB and then so the greater side of angle B. would be the greater side of angle C,
Mm-hmm.
and then, so then,
Well, okay, I'm gonna suggest maybe you were thinking that these two are supplementary, which is, you could maybe make that work. That's a possibility. Anybody see, maybe, there might be a slightly more direct way of doing this, Emma?
Do you use one of the diagonals
Okay,
to say that that's a transversal?
okay, let's use, okay, yeah, let's use one of the diagonals. So if we use one of the diagonals, that's a pretty easy one to use because we get a bunch of stuff there, don't we? Automatically we get a side congruence by reflexive property, right? I won't even write them down, but you get that's fair to do. And then we've got parallel lines cut by a transversal, so just like before, we could say we've got, actually we didn't do it this way before, but we could, because we could use conalt, right? That I just told you about, so it's the converse of one of our proving parallel lines congruent to show that those are congruent, right? If parallel lines, then alternate interiors are congruent, right? Does that make sense? So if those are congruent, then we got side angle side, don't we? And we've got a triangle here congruent to triangle there, okay? Make sense? And that means we get a ton of stuff. That's a gold mine. Once we can show triangles are congruent, we got lots of stuff, right?
Yep. Then we can just say that the side AB is congruent to side BC and
There you go. There you go, exactly. So then we could just say, okay, now we know once we prove these triangles congruent, by CPCTC, we could say that, right? And we just proved that if opposite sides are congruent, then parallelogram, right? So we got it. Does that make sense?
wait.
Yeah.
There's one column where, how to prove that two triangles are the same, CPCTC?
Well, no, we proved the triangles are congruent by side angle side, right? SAS,
Oh,
but
so
then,
then we proved that BC.
yeah, then all the other corresponding parts that weren't already used would be congruent by CPCTC, right? Does that make sense? Okay. How much time do we got?
5 minutes.
5 minutes, okay. I think, let me ask you this. How could you prove, okay, what if I gave you, I'm not going to do a specific example, but what if on the coordinate plane, I gave you 4 coordinates and I wanted you to show that those 4 coordinates are the vertices of a parallelogram, or they're not?
The slopes of the,
Okay, so if given 4 coordinates, we could just look at the slopes connecting all of the points, right, and see if they end up being 2 pairs of parallel lines, right, or segments, right? Okay, that's one way we could do it. What's another way we could do it?
the distance.
Okay, we could use the distance formula to find the lengths of each segment, and what would have to be true for it to be a parallelogram? Okay, so 2 pairs of lengths would have to be equal, right? Okay, good. Probably it for now. I don't think we don't know tricks we can't do. Yeah, okay, good. I think we're good.